Blaise Pascal was a French Renaissance polymath who got a lot done in his relatively short lifetime of 39 years. But given that you're watching this video, you probably know him for his triangle. This triangle comes from a pretty simple rule. Each term is a sum of the two above it. Now that's very straightforward, so no hate to Pascal, but drawing this triangle isn't really that impressive, especially given that he was far from the first person to discover it. The first person credited with that was Acharya Pingala 2 millennia before Pascal, and many other people also discovered it independently, including Persian scholar Al-Karaji about a millennium ago and Qian Xie in the early 11th century. However, Pascal's name is most frequently attached to this triangle in the Western world due to him writing a whole book about it, called Traité du triangle arithmétique, where he considered some of the uses of the triangle, which we'll recap quickly in case you're unfamiliar. The first application is in the realm of probability and statistics, and is best explained with an example. Let's say you flip an unbiased coin 4 times. What's the probability of getting exactly 2 heads? Well, there are 16 different possibilities, since each coin flip will either result in heads or tails, and we do that 4 times. But how many of those have 2 heads? Well, this case is small enough that we can literally just count and get 6. So our probability will be 6 out of 16, or 3 out of 8. But this isn't just some random contrived example. It's special enough that it gets its own notation. The value here is 4C2. The number of ways you can choose 2 objects from a group of 4. Generally, we write NCR to mean the number of ways of picking R objects from a group of N, and it even has its own fun formula. But if you're feeling lazy, you can just find it in the triangle, as the second element in the 4th row, given that we start our indexing at 0. Another place these numbers are useful are in expanding binomial expressions raised to a certain power. The coefficients of your terms are the entries in the corresponding row of Pascal's triangle. Now, really, this is the same application as before, since the 6 in front of the x squared y squared is just reflecting the fact that there are 6 ways to pick 2 x's when expanding. Now, given that he worked all this stuff out, you might think Pascal was a pretty smart person. But you'd be wrong, because this is where he stopped. He wasn't thinking big enough. He just didn't have the vision. He was part of the 99% of gamblers that quit before they win big. What am I on about? Let me introduce you to Pascal's pyramid. Yeah, we got another dimension now. Now we'll start simpler with a square-based pyramid instead of a tetrahedron, just because the visualization is a little easier. So, as with before, we start with 1 at the very top. But instead of this one donating a copy of itself to the 2 points below it, a copy of itself goes to each of the 4 vertices of the squares beneath it, like so. And we can continue this trend for the next layer, and the different coloured mini 1s show you which big one it came from, and it's pretty easy to keep on going downwards. You basically just fill in each gap with the sum of the 4 numbers surrounding it. And so now we have a bunch of layers, there's one big question we should be asking. How does this relate to our choose function from before? And then, as a sort of extension I suppose, how does this relate to polynomials? The general pattern within a layer here isn't too hard to spot, and I strongly recommend that you pause for a moment to try and work it out. Hopefully you've spotted that each number is the multiple of the 2 numbers in its respective row and column. And so if we let n and m index our row and column respectively, then each number on layer k is just kcn times kcm. For example, we're looking at layer 5 right now, so the number in the 3rd row and 1st column is going to be 5 choose 3 times 5 choose 1, which is just 50. So moving on to the extension, it's clear that this has something to do with multiplying 2 binomial expansions together. But it's not as simple as before, as we have more numbers in each layer than we do coefficients for our expansion. Well, let's write this out again, but take our time with grouping like terms together. Boom, there we go. Not only do we have the right number of terms, but it's even all arranged neatly in a grid. And we can see that when we combine the like terms, we're adding up the coefficients along the diagonals. But Pascal wasn't missing out on much with this one, because it's something that his triangle could already handle. In our case, all we've done is calculate x plus y to the 4 in a needlessly difficult way. But let's try a tetrahedron, and I promise you this one is actually good. Again, we start with the lone 1, but this time a copy of itself goes to each of the vertices of an equilateral triangle. Again, we repeat this, and we get more and more triangular layers. Again, I recommend that you pause and see if you can figure out the pattern yourself. Now this one's a little trickier to spot, but each layer is just Pascal's triangle up to a given point, but then each row is multiplied by the numbers in the bottom row of the triangle. Now, that's a little wordy, but hopefully with it drawn out it all makes sense. Now for the real question, what do these numbers actually mean? Again, I think it's worth pausing to try and puzzle this one out for yourself, because this is easily the most satisfying one to figure out. Alright, now for the reveal. In the same way that the triangle gives you the binomial coefficients, the pyramid gives you the trinomial coefficients. Let's take x plus y plus z cubed. If you take the time to expand it out fully, you get this. And if I rewrite it like this, suddenly it looks very, very familiar. And this is how it works for all of the layers. Each corner is just x or y or z to the n, and then the power of each variable decreases as you get further away from said corner. And as with before, there is a formula for all of this. In this case, I'll rate it as NCR, Q to mean that we're choosing one group of R and one different, mutually exclusive group of Q. And we can actually think about this using our current choosing function. We would have that n choose R, Q is n choose R times n minus R choose Q, since when we pick the second time, we've already removed R elements from the group we can choose. And then, this can be simplified down to this expression. And indeed, this can be extended to any number of variables. If you have n choose some variables, then the value is going to be n factorial over the product of the factorials of your variables times n minus the sum of all your variables factorial. So, for example, if you were calculating v plus w plus x plus y plus z to the 10, then the coefficient of the v cubed w squared xyz cubed term would be this here, which is equal to 50,400. But if we take a step back from the practical side, what we found is this crazy connection between geometry and a bit of combinatorics, which also links to algebra. Because if you simplify things to the 1D case, where you just have a line, and each time you go down you just get 1 again, then you get the monomial coefficients, and I'm like 99.9% sure that when you reach the 4D version of a tetrahedron, which is called a pentacheron or something like that, you get the coefficients of a quadrinomial expansion. Of course, practically this would be a pain because, well, it's 4D, but since we only care about one layer at a time, we could try this. We just have to draw out tetrahedrons, and we can do the first few, and you can try this yourself if you have a lot of time to kill. But anyway, what we found is this pretty significant connection between n-nomial expansions and the simplest shapes in n dimensions: lines, triangles, tetrahedra, and whatever the technical terms are for all these hypertriangles. Now, I don't know if there's anything meaningful that actually comes from this, but at the very least, it is pretty cool. Thanks for watching.